Now we will solve some of the engineering mechanics GET problem. So let's take engineering mechanics GET ME 2009 problem. So first I will write the problem. So just I am writing the problem. A uniform rigid rod of mass M and length L is hinged at one end as shown in figure as shown in figure. A force P is applied at a distance of 2L/3 from the hinge so that the rod swings to the right. Find reaction at the hinge. So it is a GET problem which is asked in GET ME 2009. Problem: a uniform rigid rod of mass M and length L is hinged at the one end and a force P is applied at a distance of 2L/3 from the hinge so that the rod swings to the right. Now we have to find out reaction at the hinge. Now I am drawing the diagram here. This one is the hinge, and on hinge we are having the rod of length L, and here we are applying force P at a distance 2L/3, and we know the mass of the rod is given, that is M, and now we are interested in reaction at the hinge. So let's assume the reaction at the hinge is R, and which is acting in a negative x direction. So if we see the motion of this system, so the rod will rotate about this point O. So we can apply the D'Alembert principle for converting this system into dynamic equilibrium. So if you see, there is only one disturbing torque will act at a point O, and we can easily calculate this disturbing torque, that is P into 2L/3. So the torque we can easily calculate, that is P into 2L/3. That is the torque. And now, according to the D'Alembert principle, this torque, if we apply this torque along with the inertia torque, then the body will be in dynamic equilibrium. So I can write this thing. This is torque, suppose this is T. So T minus I alpha will be the inertia torque. So according to the D'Alembert principle, we can write T minus I alpha equals to 0. So we know the T, that is P into 2L/3. And now we are interested in I, means moment of inertia of this rod about an axis passing through O. So it will be mL²/3 into alpha equals to 0. And if we solve this thing, we will get P to 2L/3 equals to mL²/3 to alpha. So now we will get 2P/mL equals to alpha. So the value of alpha we are having 2P/mL. So we got this alpha. Alpha is nothing but angular acceleration. So now we can easily find the linear acceleration. So linear acceleration. So we know here the mass will be acting at a distance of L by 2. So we can easily find out this thing. Linear acceleration, it is A equals to alpha into L by 2, because the center of gravity will lie at a distance L by 2. So now A equals to 2p by ml into L by 2. So we will get 2 to LL cancel. So p by m will be the acceleration. That is linear acceleration. Linear acceleration. So now we can apply the D'Alembert principle for the linear motion. So on application of D'Alembert rule for linear motion. So if you see here, P is acting in positive x and R is acting in negative x. So net force who is responsible for linear motion will be P minus R. So P minus R, that is the net force. And now according to D'Alembert, we have to apply the inertia force in a direction opposite to the direction of motion. This one is the direction of motion here. So we will apply the inertia force in opposite direction, means minus x. So minus, and inertia force will be m into a. I am taking a here because we are considering the linear motion. So I can write p minus r equals to ma, and we know the value of a. So I can further write p minus r equals to m. The value of a is p by m. So we will get p minus r equals to p. So from here we will get r equals to 0. So the correct answer for this problem is r equals to 0. Let's take another gate problem which is asked in gate 2008. So EM gate AME 2008. I am just writing the problem. A straight rod of length LT hinged at one end and freely extensible at the other end rotates through an angle theta t above the hinge at time t lt equals to 1 meter per second, that is velocity. Similarly, theta t will be pi by 4 radian and theta t angular velocity 1 radian per second. Now we have to find out the magnitude of velocity at the other end of the rod. So I will just repeat the question. Here the straight rod of length L is given, that is hinged at one end and freely extensible at the other end. It rotates through an angle theta above the hinge. At the time t, the LT is 1 meter and the corresponding velocity is 1 meter per second. Similarly, theta at t is pi by 4 radian and angular velocity is 1 radian per second. So we have to find out magnitude of velocity at the other end. So now let's solve this problem. So I am just drawing the problem here. one end of the straight rod is hinged at one end and other end is free, and we know the other end we are having the velocity is given, that is 1 meter per second, and now it is rotating with 1 radian per second, that is the angular velocity, and the length it is L, that is 1 meter. So now we are interested in this velocity, that is suppose V. So according to the relationship between V and omega, I can write V equals to omega R. Here omega is given 1 radian per second and R in this problem is 1 meter. It is nothing but the length of the rod. So V, I will get 1 into 1 equals to 1 meter per second. So here we are having velocity V, that is 1 meter per second, and here we are having another velocity that is 1 meter per second, and now we are interested in the resultant of that. So let's suppose that is this point is A and suppose this point is B, so I am interested in VB. So that is suppose VB means the velocity at the point P, that is the other end. So VB I can write equals to square root of V square plus 1 square. So VB equals to V square means 1 square plus 1 square equals to 1 plus 1 is to root 2 meter per second. This one is the velocity at the other end of the rod. But velocity is a vector quantity, so we are also interested in this angle, that is theta, which is making with the horizontal. So theta equals to tan inverse of V by 1 equals to tan inverse of value of V is 1 by 1. So tan inverse of 1, I will again write theta equals to tan inverse of 1. So we will get 45 degrees because tan inverse of 1 is 45 degrees. So by this way we can get the direction as well as we have already got, that is root 2 meter per second. So correct answer for this problem is root 2 meter per second. Let's take another problem which is asked in GATE 2008. So EM GATE ME 2008. So first I will write the problem. A cantilever type gate hinged at Q is shown in figure. P and R are the center of gravity of the cantilever part and counterweight respectively. The mass of cantilever part is 75 kg. Find mass of counterweight for static balance. I will again repeat this problem. In this problem, a cantilever type gate is given which is hinged at Q. P and R are the center of gravity of the cantilever part and the counterweight respectively. And the mass of cantilever part is given, that is 75 kg. So now we have to find out the mass of counterweight for static balance. So let's solve this problem. So for this I am drawing the diagram also. This one is a kind of cantilever gate. I am just drawing whatever given in the problem. Here this one is the hinge, this hinge joint. There are two points P and R. At point P, the mass of the cantilever is concentrated. That is the point P. This one is the point R. So mass of the cantilever, we know that is 75. So weight is 75 into 9.8. Here at R, the mass of counterweight. So I will write MC. So let mass of counterweight is MC. So the weight will be MC into G. And they have given this distance. This distance is 0.5 meter and this distance is 2 meter. And now for this problem we have to find out MC. So our interest is MC. So now for this problem they have mentioned we have to find out mass of counterweight for static balance. So we can apply the conditions of equilibrium. So let's apply the conditions of equilibrium which is based on moment. That is algebraic summation. All moments above Q should be 0. If we see the moment at Q, so here moment due to this R will be R into the distance, perpendicular distance is 0.5, and it is moving in anti-clockwise direction. So anti-clockwise direction is negative and clockwise direction is positive as per our sign convention. So anti-clockwise, so negative. Due to this P, movement at Q will be P into this distance, that is 2 meter. So P into that is, I will again mention here, that is R. In place of R I have to write, sorry, I will again calculate this moment. Moment due to this MCG at Q will be MCG into 0.5, that is perpendicular distance is 0.5 here, and the direction of the movement is anti-clockwise, so negative. Movement due to weight 75 kg, that is 75, and weight will be 75 into 9.81, and perpendicular distance here is 2. So 75 into 9.81 and perpendicular distance is 2, and the movement is in clockwise direction, so positive equals to 0. I will again repeat, here I am applying the conditions based on movement, that is algebraic summation of movements of all the force above Q should be 0. Q is a hinge, but I am not considering the reaction here because the movement due to reaction at Q will be 0 because the perpendicular distance is 0 here. So now I am directly considering the moment due to MCG. So MCG into perpendicular distance is 0.5 and it is moving in anti-clockwise direction. Similarly, moment due to this 75 kg weight. So weight is 75 into 9.81. Perpendicular distance is 2 equals to 0. So now MC into 9.81 into 0.5 plus 75 into 9.81 into 2 equals to 0. If I further simplify, then I can write MC into 0.5 plus 75 into 2 equals to 0. So here I will get MC into 0.5 equals to 150. So MC will be 150 by 0.5 equals to 300 kg. So the correct answer for this problem is MC equals to 300 kg. Take another problem which is asked in GATE 2008. So EM GATE M 2008. So first I will write the problem. A circular disc of radius R rolls without sleeping at a velocity at a velocity v. The magnitude, now we have to find the magnitude of the velocity at point P. At point P is shown in figure. So I am again repeating the problem. Here a circular disk of radius r is given. It rolls without slipping at a velocity v. And now we have to find out the magnitude of velocity at a point P shown in figure. So I will just draw the diagram. Here there is a circular disk. The radius is r here. And we are having the point P here, which is making an angle 30 degree, and which is moving with a linear velocity v. And suppose this point is O. Now we are interested in velocity at point P. So we are interested in Vp. So now if you see this diagram, then we can say that the O is the instantaneous center at this moment. Means instantaneous center, O meaning is that the disk will be in a pure rotational motion above O at this instant. So we can easily find out the angular velocity at that instant. So the angular velocity at that instant we can easily find out if we know this thing. This thing we are having r. So now angular velocity equals to omega equals to v by r. So here we are having the velocity v and corresponding distance is capital R. So v by r. So now we are having v by r. That is the angular velocity. Now we have to find out velocity at p. So for velocity at p, then this one will be the velocity at p here, which is perpendicular, which will be like that, tangential to the dead. Or I will again draw the diagram here. Here we are having the point O here. Here we are interested in this P. And we know here the distances. Here this angle is 30 degree. And we are interested in VP. So this will be the at the moment perpendicular to the OP. So this is VP. So now we have to find out VP. It's nothing but omega into OP. So our major concern now how to calculate OP, because omega we know that is V by R. So we have to find the value of OP. Why I am taking distance from here? Because O is the instantaneous center at that moment. So at about O, the disk will be in pure rotation. So that is the point of rotation, and that is the point where we are interested in linear velocity. So we have to take OP. So now I am again drawing the diagram for our understanding here. This is this thing. Suppose this point is A. We will write A. This is O. And now we are interested in OP. So here, if you see the diagram, this angle we know here that is 30 degree. And if you see the angle here, this angle, this is 90 degree. So now the remaining angle, this is R, this is R. So both will be the same. So the remaining angles here, it is nothing but, it is 90 plus 30, 120. So these angles will be 30, 30. 30, 30. Now again, I will again draw the diagram here. This is 30. This is also 30. Here point A, here point B, here point A. That is for our understanding. Now if we draw a perpendicular from A on OP, it will be like that. Suppose this point is B. So now we are having AOB right angle triangle. So we can easily, this is R, this is R. So we can easily find out OB. The value of OB is nothing but R cos 30 degree. Similarly, the value of PB is nothing but R cos 30 according to the diagram here. So OP is nothing but OB plus BP equals to R cos 30 plus R cos 30. So it will be 2R cos 30 degree. So we will get 2R cos 30 is nothing but root 3 by 2. So I will get root 3R. Now if we put the value of OP here in VP, that is VP equals to omega into OP. Omega we have already calculated, that is V by R. OP is root 3 by R. So I will get the value root 3V. So the VP equals to root 3V. This one is the desired answer. So the correct answer for this problem is VP equals to root 3